Okay, let's dive right into this. Imagine taking an artificial intelligence that has just consumed all the chaos, the noise, the sheer volume of the entire internet and trying to transform it. We're trying to take it from this wild, unpredictable generalist into a precise, laser-focused specialist. Honestly, it's one of the most fascinating engineering challenges of our time. We are talking about taking a sprawling digital mind, this massive mathematical structure containing billions of parameters, something that has absorbed trillions of tokens of text, and paring it all down to do exactly one thing perfectly. This machine literally holds the entirety of human knowledge. But here's the catch. Without restraint, that infinite knowledge is practically unmanageable. Think of it this way. Picture a scenario where you've just hired a scholar who has memorized every single book ever written in human history. I mean, they're undeniably brilliant. But when you ask them to simply sort your emails into important and spam, they start reciting 14th century poetry. Or maybe they just start mimicking your exact writing style instead. Why does this happen? Well, because raw foundational AI models are fundamentally just statistical pattern matchers. They aren't actually trying to answer your prompt. They're just trying to complete the document based on the statistical likelihood of what word comes next in their massive training data. So the scholar is undeniably brilliant, but they are completely useless for the job you actually need done. For the creators of artificial intelligence, this exact scenario was an incredibly expensive, frustrating nightmare when dealing with raw foundational models.
Welcome to the overview effect, where you zoom out and everything changes. So here is the million-dollar question for this explainer. How do you turn a machine that has read the entire internet into a machine that does exactly one thing? To really understand this, we have to transition our focus away from the brute force furnace of pre-training and move into a phase of strict surgical restraint. Let's just quickly remember what that furnace of pre-training actually is. It's an era of totally unsupervised learning. For months, supercomputers simply feed the AI vast oceans of internet text without any human labels, without any rules, and without any specific goals other than to blindly absorb and predict the next word. But as we've seen, raw intelligence without boundaries completely lacks true utility. And this brilliantly illustrates what engineers call the generalist problem. You see, after spending millions of dollars and weeks of supercomputer time, the resulting foundation model doesn't actually act like a helpful assistant. Instead, it acts like a chameleon. It perfectly blends into whatever text you hand it. Let's say you give it a very specific task. You type in, "Is this email spam?" The model might just reply with, "Is this email urgent?" It doesn't answer you because it thinks it's just generating a list of questions based on a pattern it saw on a random forum 3 years ago, right? It wants to continue the internet's text, not solve your specific problem. So to fix this, we have to enter the third major phase of the AI pipeline. We enter fine-tuning. Fine-tuning is the process of taking a massive, generalized foundational model and applying targeted training to make it perform a narrow, highly specific task. But how do we actually pull that off? Well, we introduce highly structured datasets. Instead of feeding it the raw, chaotic internet, we feed it high-quality, human-curated examples. These are instruction datasets filled with perfectly labeled data that show the model exactly what correct looks like. Because if you want the machine to stop predicting patterns and start making definitive decisions, you can't just ask it nicely. You have to physically alter its anatomy and meticulously train its new structure. Ultimately, the difference here is fundamentally about utility. A raw foundational model is kind of like a massive Swiss Army knife, but with thousands of glowing, shifting blades. It can do a little bit of absolutely everything. It can translate French, it can write code, it can tell jokes, and it can explain quantum physics. But because it has so many blades, it is incredibly unwieldy for a specific, delicate task. Fine-tuning takes all of that sprawling, unfocused potential and hones it down into a single, perfectly sharpened scalpel. We are transitioning this technology from a chaotic generalist that tries to please everyone into an elite specialist built for one single purpose. Now, there are several ways to fine-tune a model, but today we're going to explore the most extreme method. It's called classification fine-tuning. In the world of AI, classification simply means sorting data into predefined buckets: spam or not spam, fraudulent or safe, positive, negative, or neutral. We are going to take a machine designed to speak 50,000 different words across dozens of languages, and we are going to force it to only ever speak 2 or 3. We are going to perform digital brain surgery. If you look at the physical architecture of a large language model as it evolves, you'll notice a massive divergence happens. We are taking that huge, pre-trained foundation model and completely splitting its evolutionary path. One path might remain a generalist, sure, but our path breaks off to become a highly specific classifier. To understand how we actually achieve this divergence in practice, we really need to look closely at the physical anatomy of the AI itself. We need to open up the black box. Let's imagine the model as a 12-story transformer tower. When raw text data flows from the bottom floor up toward the top, it passes through incredibly complex mathematical layers called attention mechanisms and feed-forward networks. Now, these bottom 11 floors, they do all of the heavy lifting of comprehension. They are packed with billions of mathematical weights and parameters that basically act as the structural beams of this tower, holding all the knowledge the AI learned from the internet. They process grammar, context, facts, and the subtle, weird nuances of human language. They are the deeply knowledgeable reading part of the machine's brain. But the very top layer of the tower, the 12th floor, is entirely different. It's the output head. You can think of it as a sprawling array of 50,000 tiny satellite dishes. Each dish represents a different word or token in the model's vocabulary. When data finally reaches this top floor, these dishes light up with different mathematical probabilities. For example, the dish for the word apple might be glowing with a 90% probability, while the dish for banana is only glowing at 10%. This top layer acts as the machine's vocal cords, translating all that deep structural comprehension from the lower floors into the probable words it actually speaks back to you. So to create our specialists, engineers do something incredibly blunt. They take the code for the foundational model and they physically sever the output head. In technical terms, they literally delete the final mathematical output layer, often called the linear head, entirely. It is simply wiped from the architecture. The machine's vast intelligence, its deep understanding of human language, tone, and context, remains completely intact and frozen inside the lower 11 floors. But suddenly, it has no physical way to express it. The vocabulary is gone. The vocal cords have been surgically removed. Now, instead of throwing away the millions of dollars and countless hours spent teaching the AI to understand text on those bottom 11 floors, all that complex, rich data is repurposed. All of that incredibly nuanced contextual understanding is squeezed into a mathematical bottleneck. It gets funneled into a grand view, highly restricted decision-making point that only outputs a single probability. We don't teach it how to read from scratch, we just teach it how to vote. Right after severing the old output head, engineers attach a brand new classification head. And this is where the magic happens. Instead of 50,000 vocabulary words, this new head might have exactly 3 nodes: positive, negative, and neutral. And here's the truly brilliant part. Because engineers freeze the bottom 11 floors and only train this tiny new classification head, they can create an elite, specialized model for a mere fraction of the computational cost of training a completely new AI from scratch. The AI uses all of its vast, pre-trained internet knowledge solely to figure out which of those 3 precise nodes to light up. So the flow of data is now entirely linear, locked into these strict constraints. The machine can't ramble, it can't hallucinate a poem, and it certainly can't act like a chameleon anymore. But we still have to run a training loop, so this new head knows what to do. We feed the model thousands of carefully labeled examples. If we feed it a happy review and it accidentally lights up the negative node, the system calculates the error, what engineers call the loss. It then uses a process called backpropagation to mathematically adjust the weights in that tiny new head, teaching it to be more accurate next time. It literally takes everything it knows about the universe and compresses it into a single forced choice. We gave the machine a voice, but now we have to teach it how to listen. So what should you really take away from this explainer? When you look past the illusion of a specialized mind, you realize something pretty profound about how we build these digital tools. True utility is not about knowing everything. It is about taking infinite knowledge and focusing it into a single perfect point. That is the true hidden power of fine-tuning. We build gods of information and then we painstakingly bind them, because an unconstrained mind is just noise. But a focused mind can actually change the world. Welcome to the overview effect, where you zoom out and everything changes. If this changed how you see things, make sure to subscribe to the overview effect. New perspective every week. Thank you for joining us on this explainer, and we will see you in